Welcome to the Math Record. Today I'll be covering the concept of limits. This video will cover part 2 of chapter 1 in our calculus class. For starters, I will want to notify you that generally in calculus, the idea of limits isn't used as much. This doesn't mean that they're unimportant, but most of the basics could be done with the concept of derivatives, which we'll cover in later math record videos. Okay, let's start with learning limits. So, limits. The idea of limits is basically the value as something approaches it. So, usually this is done by, let's say you have like a linear graph, right? So, let's say the graph is y is equal to x, and you say x over here is equal to 5, right? So you have this point. So you want to find the value of that y. So as x approaches 5, what would be the value of that y? Well, if you did any algebra, basically it's very simple. We would say y is 5, because you just plug in 5 to equal to y. This is the correct answer. But usually the idea of limits is that what is proper notation is that you write x, the limit, lim. You don't have to write the entire limit name. It's just lim, which you have x, and then you write an arrow sign as it approaches 5. Then you write the equation. You don't have to write the y, so you just have to write x, right, as x. If this is 2x, just write 2x. So so the limit as x approaches 5, which for x would be 5, where you just plug it in. So that's the basic idea of limits. Um, So the easiest way for these limits is that you can always plug in those answers to get the value. As I said, with like y is equal to x, we just plug in 5 for x to get 5. Um, the general idea to find these limits instead of plugging them in is that you plug in very close numbers. So let's say we have y is equal to x, right? Back. So instead of plugging x is equal to 5 to get when y is equal to 5, and when y is equal to that, what f of 5 is, right? Let's say this is f of x is equal to x, right? Instead of y, it's the same concept. If you plug 5 in, what happens as x approaches 5? So instead of putting in 5, we plug in really close numbers. So let's say we plug in numbers like 4.5, like 4.9, 4.99, or we have like 4.999. Like we have really, really, really close numbers to 5 to find these really close approximations to y. So you plug these in, right, you get 4.5, 4.9, 4.99, and 4.999 for y, right? So so it seems like it's approaching a number, and it seems to be increasing, so as you logically assume, it should go to 5. And that's the general idea for limits. You can also, instead of choosing numbers like lower than 5, alternatively, you can also choose numbers that are higher than it. So let's say you choose something like 5.5, or like 5.01, or 5.001, or 4.0001. You get really, really close numbers to 5 that are above it, and we can see that as the numbers are above it goes down, it seems to be approaching, going down from like 5.5 to get closer to 5. It seems to be approaching 5, right? So if you plug it in, and that's the general idea for how these work. So this might seem somewhat confusing because I'm using the concept of the equation y is equal to 5. So y is equal to x. So let's change this to like y is equal to 2x minus 1, right? So let's make somewhat of a table. And let's just have few numbers. So let's say we want x is equal to 5, right? We want to find when limit as x approaches 5. So let's choose like a really small number. Let's say we have 4.5, right? That's below it. And then we can have 4.9, right, as very close to it, and then something above it, let's say 5.1, or and something way above it, which is like 5 point, let's say 5, right? Or and then we could have like 6 or something, right? So if we have 4.5, we could plug that in. That makes 9 minus 1 is 8. 4.9 times 2 is 9.8 minus 1 is 8.8. We have 5.1 times 2 minus 1, which is 10.2 minus 1, which is 9.2. 5.5, which is 11, so that makes 10. So that's 12 and that's 11, right? So we want to find 5, right? Which is between these two numbers. So as you see, as your x value, this is your x and this is your y, as your x approaches 5 from this side that's smaller, then basically it seems to be going up in value as it goes up to 9, right? And if you see from numbers that are above the 5.5 for x, then as the numbers lower down, it's from 11 to 10 to 9.2, it seems to be also approaching 9. So you see how that they are approaching 9 as the answer, which you could also put 5 into that equation. So 2 times 5 is 10, minus 1 is 9, which is true. So the idea that we could use these really, really close numbers to approximate those answers for limits is generally the idea how we use this. It might seem strange to use these for equations like these, but this is a very simple case in which we could always expand these ideas for like a smaller for like much more complicated equations. Let's say like we have y is equal to sine of x, and we want to know what happens as x approaches like 2, you know? Or like, sorry about that. We have sine of x divided by x, and you want it to happen when x approaches 0. Um, for the for these examples, you can't plug in 0 into the x because then it will be undefined. Because sine of 0 is 0 divided by x is when x is 0 is just 0 divided by 0. So you cannot have that happen. But there's technically is an answer. So you should find so there should be a numerical limit to this in which we will use the concept of using these small like increments that are not really 0 but really really close to it, like 0.000001 or something, or you could keep adding even more zeros to get even more precise answers. And that's the concept of like limits. So uh like for these examples, instead of like using these trig functions, let's try something like we have limit as x approaches 1, right? And we have x squared minus 3x plus 2 divided by x minus 1. Usually for these questions, there should be they should be able to factor each other. So if you plug in 1 here, right, that's 0, and you plug in 1 here, that's 1 minus 3, which is minus 2. Minus 2 plus 2 is 0. So that's also 0. But it doesn't matter what's on the top. It matters on the bottom. So if 1 puts into x minus 1, that's 0. That's already going to be undefined. So the point is that you can't plug in 1 to get a really simple answer off the bat. So what you do is that you kind of factor them. So how do you factor x squared minus 3x plus 2? Which you get x minus 1 and x minus 2, right? So that's x squared minus 2x minus x, which is minus 2x minus x combines to make minus 3x, and then negative 1, negative 2 makes 2. All over x minus 1. So you see how you see these factors could cancel out? You can cancel those out and you have x minus 2. So this is the same thing as saying limit as x approaches 1 as for x minus 2. So you plug in 1 here, you get negative 1. And that's your answer. The limit as x approaches 1 for x squared minus 3x plus 2 over x minus 1 is negative 1. And that's the general idea of like how these work, even though you see that you can't plug it in. Usually, this works for calculus classes, but sometimes they won't. And there would be future concepts that will be able to solve these ideas that aren't able to fully factor these equations out. Like, let's say we have limit as x approaches 1, right? And you have x minus 1 all over x minus 2 and x minus 3, right? You can't factor any of these equations out, so there's no way for you to actually solve them. But there are future concepts which we'll be able to touch upon these ideas and see how they work. Okay. Other than using polynomials, there's also ways for radicals, which usually are some of the trickier questions. So let's say now we have limit as x approaches 1, and you have something like x minus 1 all over the square root x minus 1, right? So you plug in 1 on the bottom, that square root 1 is just 1, so 1 minus 1 is 0. But there's a radical, so how do you take that on the bottom? So usually what you do is that you want to always multiply by like the conjugate of the denominator. So how this works is basically whatever value you see for the variable, basically just write the same thing. So you have square root x, just write square root x, and then you choose the opposite of whatever is next. So you have -1, the opposite of -1 is +1, right? And then you kind of multiply these values together. So remember this, and then you multiply by square root x plus 1 all over square root x plus 1, right? Because technically square root x plus 1 over square root x plus 1 is just basically 1. So you're multiplying this equation by 1, so it's basically not changing anything. So as you learn in pre-calculus. So the idea, let's say we have x square root x times square root x is just x. Square root x plus 1 is square root x. Square root x times -1 is negative square root x. And then -1 times 1 is -1. And you see how these cancel out? And that's why we keep the first term the same, and then we keep the second term the same. I mean different. You can also choose the first term as different and then keep the second term the same. It doesn't matter. All you need to do is that you need to cancel out these radicals. You see how that works? You have a positive square root x and a negative square root x, and we can cancel those out, right? And then you're left with x and -1. So on the top, let's just leave that alone. You have x minus 1 times square root x plus 1, right? All over, you have remaining x minus 1. And you now see like a similar numbers. So you have x minus 1, you could cancel those out. So all that's remaining is square root x plus 1, which is equal to this equation, right? So now you just have limit of x approaches 1, and then you just plug in 1 into the equation. So square root 1 is 1, 1 plus 1 is 2. So the limit of x approaches 1 for x minus 1 over square root x minus 1 is basically just 2. Even though it might seem very challenging, this is a really simple solution of how it works using conjugates. So for these types of questions where it seems like it's undefined, you might just want to find out what's in the denominator and then find out if you could factor anything out. And that usually works. So that's basically covers the general idea how to find limits. So now let's move on to limits for trigonometric functions. Let's say have like a basic example. Let's say we have something like limits as theta. Theta stands for an angle, which as it approaches pi all over 6. For calculus, you're always going to be using radians. If you don't know what radians is, you should probably search it up, and I think we also covered it in our pre-calculus class. So for radians, we're going to use radians and not degreeses. So radians is better than degreeses. Because degreeses are something we arbitrarily make up for like 360 degrees. The reason we chose 360 degrees for our complete like circle is because 360 degrees is simply divisible by a lot of numbers. So like by 2, 10, 6, and 4, and like a bunch of like other like 3, like a bunch of numbers. So that's why we chose 360. And but that is very arbitrary and we don't like to use them. So for that reason, we usually use radians, which is a really good measurement of how it works because it deals with like a actual numerical amount that calculus could work with, which is 2 pi, because the circumference of a unit circle of a circle basically is 2 pi. Because let's say you have radius 1, right? The formula for a circle is 2 pi radius for a circumference. So if radius is 1, the circumference is 2 pi. So you could have 2 pi. So if we have like pi over 6 radians, right? Then basically we have one line right here, and then pi over 6 would just be, if this entire thing is 2 pi, then basically halfway is pi, so a sixth of that would just be like right here, and we could have only this portion of that circle, and we could use that to find trig functions, and which is the reason why we use radians. So always the general idea is that you never use degrees in calculus. You always use radians. So you always, if you ever see anything on a test, it's usually in radians. It's never in degrees because it never works in degrees. It's doesn't the math doesn't work out generally. So so going back to our example, we have something where theta approaches pi over 6 radians, okay? And let's say the equation is sine over x, right? So we have like a circle, right? Where sine of x, sine is basically the y, so we just need to work for the y coordinate. So pi over 6 is something right here, right? Pi over 6, this is pi, so a sixth of that would be like somewhere around here. So pi over 6, if you know your unit circle, basically numbers, what is you have remember the 30, 60, 90 rule basically for right triangles. Opposite of 30 is a half for sine. Opposite of 60 degrees for sine is square root 3 over 2, and 90 degrees is always just 1 basically. So sine is basically the idea of for y. So would be different if this was cosine of x. If it's cosine of x for 30, then it would be square root 3 over 2 for cosine. So don't think this is the universal rule. I'm just bringing up the idea just so then we don't have to actually do the math. So for limit as theta approaches pi over 6 for sine of x, it will be equal to 1/2. Because this is very simple, because you could just plug in pi over 6 into x to get 1/2 as your answer, which is really, really simple. So that's the general idea of how it works for trig. But for trig, there are generally two equations you need to memorize. We could prove these later on in our classes, but it's just good to know because they're the ones that are the most complicated and used probably the most often, which is limit as x approaches 0 as sine of x all over x. I used this example earlier, which is, let's say we have 0, right? As you have x is equal to 0, then that's just 0. That's undefined, so you can't do anything about it. But the general idea for this solution is that this is equal to 1. It might seem weird, but there are numerous proofs where you could use this to prove it. So one method is called the squeeze theorem. Squeeze, squeeze theorem. We won't be teaching this in this class because we don't find it as useful as much. So if you want to search this up, you could. But basically it uses this one. So one of the ideas that could prove it is the squeeze theorem. There's also other ones that are a little bit more simple, which we will focus on later on. They're not really proofs, but more of general ideas of how it could be like derived. And this is for sine. Now now think of the idea for cosine. So if limit of x approaches 0, we have cosine of x minus 1 divided by x is equal to 0. Or if you want to be more precise, instead of x, we could write theta. So x, this is theta. Usually I just write x. Usually the notation isn't as much as important to me, but instead you just have a variable which you can plug it in. Just remember theta should always be radians, as I said before. So that's the general idea of how these two equations work. So these are true. So these two you generally want to memorize. So how do you memorize it? Basically, just always know that the limit approaches 0, because like on the bottom is always be an x. So let me just erase those parts so we could get those x back. Okay. So we have these x's, right? Because we want them to be undefined, right? So basically we have x approaches 0, x has to be on the bottom. So for this, x is on the bottom, x is on the bottom, so it's true. So you just plug in 0 and it'll be undefined. So just leave x on the bottom. Just know that that's true. So how do you know what's on the top and how you remember what the value comes out of? So basically the general idea that I kind of remember is that you want the top portion to also be 0. So if you put sine of 0, right? Sine of 0 is 0, so you don't have to change anything about it. So just keep the sign. Now for the cosine, if you have cosine 0, that's equal to 1. So to get that 1 away, you just subtract 1, right? So you have cosine of 0, that's 1. 1 minus 1 is 0. So you have 0 over 0. For this, also, you have sine of x, which is sine of 0, is 0 over 0. So that's 0 over 0. So you just gotta keep those zeros with each other. So how do you find out what they output to? Because it's different. Basically, how I remember it is that it has to be opposite of what you got from the numerator. So you have sine of x, right? Sine of x, we said before, sine of 0 is 0. So instead of having 0, we have 1. And that's how I remember it, because it's the opposite of 0 is 1. Because those are the only two answers, 0 and 1. Now for cosine of 0, right? Cosine of 0 is 1. So opposite of 1 is 0. And that's how I memorize it. It's usually a really simple way to think about it. We just always have limit of 0, x on the bottom because you had to make it undefined. And the top portion has to equal to also 0. So if you think about cosine and how sine works and what numbers come out of it, just subtract 1 from the one that makes sense, which is the cosine of x. And then to find out what it outputs to, just find out what the original numbers come out to as a 0, 1, and just choose the opposite number of that, which you get these numbers. And that's how I remember basically these identities. For these general ideas, just memorize it for now. We'll be covering more about these later on, and we could prove it. Okay? So, usually, so basically, that covers the general idea for trigonometric limits. Besides those limits with actual numerical answers, there's also ones that don't have limits like these, which like an answer like 1, 2, 3, etc., or like negative ones, such as those. Basically, you have limits that like doesn't seem to approach anything, which is called infinite limits. This is usually the same concept as like asymptotes. So, for example, let's say we have like a case like limit as x approaches 0 of 1 over x squared, right? So if x is a really small number, right, not 0, because you plug in 0, that would be undefined. So let's say we plug in like a really small number like 0.00001 for x. As x is a really small number, it gets even more smaller as you add more zeros, right? As it approaches 0. Basically, we have x for 2. X squared would make this even smaller, and then 1 over a really small number would just make a really big number, right? So as it gets bigger and bigger, there is no clear limit. So usually when we write this, we say as limit of 1 over x squared approaches infinity, approaches 0, limit of x approaches 0, 1 over x squared approaches infinity, basically. So infinity would be a really large positive number, and then if you have something like, let's say, okay, sorry about that. We have 1 over x, right? As, let's say, usually how the graph looks is that you have something like this and something like this. So let's say you want to choose this side, right? It goes to negative infinity. If you choose this side, this goes to infinity. And how we determine which one we use is that we think about which side we want to go to. So there's two notations for this. There's a positive and there is a negative. Positive means from the right side. A negative means from the left side. So we have that graph, right? So as 0 is approached from the right side, so from this side, this is the right side. As it approaches 0 from the right side, then it goes to infinity. So 1 over x. I forgot about that. Let me erase that. 1 over x and 1 over x. this will approach infinity. And from this side, from the left, right, we have right here, as it approaches 0 from the left, it goes to negative infinity, right? So it goes down. So we have negative infinity. And these are the notations. It will use 0 plus on the top or 0 minus. Or it doesn't have to be 0, or you can have like 1 plus, 2 plus, 3 plus, negative 3 plus. The plus doesn't really have anything with the number. It basically just tells you if it's coming from the right or from the left. If it doesn't have a plus sign or a minus sign, and it's just have x as approaches to 0, like just basically that number with nothing, basically it's telling you that the limits are same from the both side. So like so with my example of 1 over x squared, we have the equation will look like this, right? So as it approaches from the left and right side, it approaches infinity. So it's basically the same idea. And that's why they have no notation for plus or minus. You could, but you don't have to. And that's the general idea for finding out limits. So usually for the plus sign, right? For like a number to a plus, which is stand for the right hand, it will be called a right hand limit. This is approaching from the right. And if it's a negative, right? Let's say 2 negative, which doesn't is not in 2 negative as I said before, but 2 from the left. It's basically called left hand limit. Is you get the limit from the left. And this is the similar idea that I used for set in the beginning of the video, where I set 4.5, 4.9, 4.99, like as that number approaches 5 from the right, from the left. And then from the right would be numbers bigger than that, which is like 5.01, 5.5, and 6. Like as it approaches, like gets smaller to 5, that'll be called a right hand limit because it's going from the right. Usually I just use my hands to think about it. I'm sorry if I like accidentally said like the opposite, but basically just use your hands. Right would be in the if you look at your right hand and you think about the number between your hands, then technically the right hand it will be the number is bigger than it. So if you go down from it, or from your left hand you go up, right? Oh, up you go to the 5. That means you have to have numbers smaller than it, but then it will be closer to 5. Where you have something from the left, which you just go down, which is larger, but then you get to 5. And that's the basic idea of how you know for the right hand and left hand limit. And if they're both the same thing, you don't have to write right hand or left hand limit. We just write a. So they're basically the same number. Generally, you want to keep the positive and the negative for right hand and left hand, so then you know how it works, because it's just more precise. It doesn't really change anything. It's just proper notation usually. So that basically covers the general concept of limits. While limits are important for the basic understanding of how calculus works by introducing the idea of a small changes over time, future concepts like the derivatives and the integral will be used more often, as there are actually more they're faster and they're quicker ways to like find these solutions rather than using limits. But remember, there are actually some questions that actually require limits, li- the sine of x over x, sometimes, which rather than using like derivative and integrals. So it's just good to understand both of them, which limits will also be revisited later on, and we'll be using constantly in class to understand how these like concepts work. Well, that basically covers everything for today. Thanks for watching, and I'll see you at the next math record.